So, welcome back to lectures on engineering mathematics 2. So, this is lecture number 45 on properties of Fourier transform. So, today we will go through various properties of the Fourier transform, mainly the change of scale property, then we have shifting properties and then dual properties, derivative theorems, convolution, etc. And also we will look into the Parseval's identity for Fourier transform. So, just to recall, in the last lecture we have introduced already the Fourier transform, and then the Fourier transform of a function f was given by this integral, the factor 1 over square root 2 pi, and then we have the function f multiplied by exponential I alpha u du. And for the sake of simplicity, we have denoted this by a function alpha, because this is the transformed function now. So, it is a function of alpha, because alpha is a parameter here. And then if you want to find the inverse Fourier transform of this for instance this f hat alpha, then we can go back to the f x. So, this is f inverse f, we will have basically this f, and then this is nothing but the function this f hat multiplied by e power minus I alpha. So, here it was I alpha, and then we have minus I alpha in the inverse transform of this f hat. So, coming to the properties of the Fourier transform, the first property is the linearity, which we have already discussed in while discussing the Fourier cosine and sine transform, and this is a common property of all integral transforms. So, because of the integral, this property that the Fourier transform of this a f plus b g. So, it is a linear combination of these two functions f and g, a and b are some constants. So, that is given by a the Fourier transform of f plus this b the Fourier transform of g, which is again trivial because of the integral. So, if you want to get the Fourier of f a f plus b g, that means a f plus b g e power I alpha u, and since it is an integral, we can break into two part and this constant can be taken out. So, here this b, and then this remaining portion is nothing but the Fourier transform of f and Fourier transform of g. So, this is a common property of all integral transforms. Later on we will see again that Laplace transform also enjoys this property. So, the next one we have this change of scale property. So, if this f hat is the Fourier transform of this f as per our standard notation, then the Fourier transform of f a x. So, that is what this is called, the scaling property. We have instead of x now we have a x. So, what will be the Fourier transform of f a x in terms of the f hat, which is the Fourier transform of this function f, and here a is naturally a non-zero number. So, by the definition of the Fourier transform, we have the Fourier transform of this f a x given by this f a x exponential I alpha x integrated over x from minus infinity to plus infinity. And then if we substitute a x is equal to t, so that we have a dx is dt, and then we can have here this f a t, a x will be just t, and then we have e power I alpha and x will be t by a, and similarly this dx will be dt by a. So, we can make this substitution in this above integral. However, the range of integration, which was minus infinity to plus infinity, that will remain the same if this a is positive. So, if this a is positive, the range of this integral after this substitution will remain the same, but if this a is negative, because we have not fixed the sign of a, in that case this will change from minus infinity to plus infinity to minus infinity, or there will be a minus sign, and then we can put minus infinity to plus infinity. So, depending on what is the sign of a, if a is positive, there will be no change in the limits, but if a is negative, then because of this a x t, the new limits, so the limits of t will have minus infinity to plus infinity orientation. So, then suppose this a is positive, then we have this situation where dt over a is coming from this dx, and then we have minus infinity to plus infinity. But if we have a negative, then what will happen, this limit will change from minus infinity to plus infinity, and then we have again a similar structure whatever is there, but now if we want to combine it in terms of this Fourier transform. So, what will happen, that when a is negative, so we can, instead of this a, we can have the absolute value of a, because so suppose this a is positive, then our integral, so the Fourier transform of this f a x will be given by this formula. So, minus infinity to plus infinity, and then f t e power this I alpha, and we have the t over a, and similarly we have d t over a there. But if this a is negative, then what will happen to this integral, again this factor here, and minus infinity to plus infinity. So, we will take minus sign there, again minus infinity to plus infinity, and then everything will be as it is. So, in the second case, when this a is negative, we have somehow this minus and a is appearing. So, irrespective of this a, if we change this to absolute value of a, 1 divided by this absolute value of a, so that will take care of the sign, because when a is positive, so if a is positive, then this 1 over modulus a will be 1 over a, and if this a is negative, then this 1 over a will become 1 over this minus a. So, in both the cases we have incorporated this in this integral, instead of this a, that we have here the absolute value of a, and then we have this 1 over absolute value of a common or out of this integral, and the remaining part is just the f t e power I alpha, and instead of the t, we have now here t over a dt. So, that is the only difference. So, just rewriting this again. So, we have 1 over square root 2 pi and 1 over. So, 1 over square root 2 pi will be anyway taken care with the definition of the Fourier transform. So, we have 1 over absolute value of a and 1 over square root 2 pi minus infinity to plus infinity, and we have then f t and e I, instead of alpha now we have alpha over a, and then we have t dt. So, as per the definition of the Fourier transform, if we go, then the only change here is that this is exactly f hat, but instead of alpha we have alpha over a. So, if this is only alpha, then this is just the f hat alpha, but now instead of alpha we have got the alpha by a. So, this is nothing but the f hat alpha over a. So, that is the scaling property we have, which says that f, the Fourier transform of f a x, then this 1 over absolute value of a will come out, and then we have this Fourier transform of this alpha over a. So, this f hat was the Fourier transform of f x, and now the alpha will be replaced by alpha over a. The another property, we have the shifting property, which says the Fourier transform of f x minus a. So, there is a shift here in x. So, x minus a, this is equal to e power I alpha a and the Fourier transform of f x. So, again if we go by the definition, we have the Fourier transform of f x minus a is equal to 1 over square root 2 pi and minus infinity to plus infinity. So, f of x minus a e power I alpha x dx. So, if we substitute here x minus a to t, that means dx is just simply dt, and there will be no change in the limit. So, we are getting 1 over square root 2 pi minus infinity to plus infinity, and this f t exponential e power I alpha and x is t plus a dt, and this is exactly what we have the f hat of alpha. If we take this e power I alpha a out of this integral, then we have minus infinity to plus infinity f t e power I alpha t dt, which is just the Fourier transform of f x. So, here again we have this result that the Fourier transform of this f x minus a is just e power I alpha a and the Fourier transform of f x. There is one more property which is called the duality property, which says that the Fourier transform, if we take the Fourier transform of f hat, so f hat is the Fourier transform of f x. So, if we take again the Fourier transform of this f hat, then we will get back to f, but with this minus alpha. So, we can just check again with the help of this inverse Fourier transform. So, we know that f x is 1 over square root 2 pi f hat alpha e power minus I alpha x d alpha, and then we just need to rename that x here, we will rename to alpha, and the alpha to x, we will just change their name. So, we have here f alpha is equal to 1 over square root 2 pi minus infinity to plus infinity f hat x e power minus I alpha x, and then we have this dx there. And now, we just replace this alpha by minus alpha. So, we have now this definition of the Fourier transform, because in the Fourier transform we are taking the positive sign there I alpha x, we have f hat x. So, this is the Fourier transform of this f hat x. So, the result is interesting, which is called the dual property. So, if we take the Fourier transform of the Fourier transform of x, then we are getting back to the f, the function itself evaluated at this minus alpha. The Fourier transforms of derivative, because this is going to be very useful for solving differential equations as discussed before, because when we take the Fourier transform of the derivative, the interesting property of these transforms are that we get the result which is free from the derivative, and this is the property which is useful for solving the differential equation. So, this derivative theorem says that if f x is continuously differentiable and this f x, so this is differentiable. So, if this is differentiable and this f x is equal to 0 as this mod x goes to 0, that means when x goes to plus infinity or x goes to minus infinity, this f x is going to 0. So, that is the additional property we are taking here, but in most of the practical problems or later on we will also realize while solving PDEs, partial differential equations, that this property is quite natural. Then we have this result that the Fourier transform of f prime is equal to minus I alpha. So, this factor will come out, and then we have the Fourier transform of f x. So, again by the definition of the Fourier transform, we will apply to this f prime x, which is f prime x e power I alpha x dx, and then integrating by parts what we are getting now here, because we have two functions. So, we will integrate naturally this f prime, that will get us to this f x, and then e power I alpha x as it is, then we have minus sign again f x and the differentiation of this e power I alpha x, which is e power I alpha x into I alpha. So, concerning the first part here, when x goes to infinity or minus infinity, we have discussed already, that is our assumption that this f is going to be 0, and then e power I alpha x, that is something which is finite. So, we have this the first part of this integration that becomes 0, and then we have only the second term. because this goes to 0, we have simple result that the Fourier transform of this f hat is equal to minus this I alpha go out here, and then this is the Fourier transform of f x. Well, so having this property of the Fourier transform, which says that the Fourier transform of f prime is minus I alpha Fourier transform of f x, we can generalize this result for the higher order derivatives. That says that if f x is continuously n times differentiable, and we have this property again that f k x, so the kth derivative of f goes to 0 up to we have k is equal to 1, 2, 3 n minus 1, then this Fourier transform of the nth derivative, that means Fourier transform of this nth derivative will be simply minus I alpha every time will come out from this Fourier transform. So, instead, so every time minus I alpha, that means I alpha power this n and the Fourier transform of f. So, that is a very simple property which can remove or we can reduce the derivatives when with the application of this Fourier transform to the derivative of the function. Well, so another interesting property which is also very much used for getting the inverse Fourier transform, and then finally to the applications of differential equations, we have the convolution of the Fourier transform. So, f, the convolution of f and g, this is the symbol we use for the convolution. So, convolution f and g, that is equal to square root 2 pi and the product of the Fourier transform of f and g. So, the property says that the Fourier transform of this convolution here is the simple product of their Fourier transform multiplied by square root 2 pi. Again by the definition we will go. So, we will apply the Fourier transform to f star g, and remember this f star g, that is the symbol we have used for the convolution. So, f star g means we have this integral here. So, f star g is nothing but the integral minus infinity to plus infinity and f y and g x minus y and dy. The important property of the convolution is this its integrand here. So, one is this f y, then another one is g x minus y. So, the limits, for instance, here we are taking minus infinity to plus infinity, but sometimes this is also known that we take the limit 0 to x. For instance, in while discussing the Laplace transform, we will take this definition of the Fourier transform for the Laplace transform, but here this is more appropriate. So, we are going with minus infinity to plus infinity because this Fourier transform is defined for the entire real axis. So, here we have minus infinity to plus infinity, and this is the special structure of this convolution integral, that we have f y and the other function is just shifted by this x minus y and then dy, and then because of this Fourier transform we have e power I alpha x and then dx. So, here the trick is that if we change the order of integration, that what will happen. So, instead of this dx dy dx there, we have now dx dy 1 over square root 2 pi, and then this product is as it is, we have e power I alpha x, and now we can segregate. So, the inner integral is over x. So, these functions will be there for the inner integral, but before that we will just substitute here x minus y to t. So, that we have dx becomes dt, the inner one. So, dx becomes dt, and accordingly the limits, because the minus infinity to plus infinity. So, they will not change now. So, we have the limits f y and then g t e power I alpha, and this x is replaced with y plus t here, and then we have dt and dy. And then we can segregate into two integrals, that f y e power I alpha y and then g t we have with e power I alpha t. So, we have split it into two integrals now, because we have the separate functions which depends on y only, then we have a function which depends on t only. So, finally, what we have that this Fourier transform of this convolution is a square root 2 pi there, and we have adjusted this 1 over square root 2 pi 1 over square root 2 pi. So, that it becomes exactly the Fourier transform of f, the other one Fourier transform of g, and we have the desired result. And sometimes it is very useful, and we will realize in many applications that if we take this inverse here on both the side, then what will happen, we have this product, the convolution product here f star g, and then we are taking the inverse. So, inverse of this f star f hat and this g hat, and this 1 over square root 2 pi will this cancel out. So, we have e power minus I alpha x, the definition of the Fourier inverse transform. And then so, what result we have now, which can be now summarized here, that this convolution basically is equal to the product and or the Fourier inverse Fourier transform of the f star g star, or from here itself we can just rewrite that the convolution f star g star is nothing but the Fourier inverse of this square root 2 pi and the Fourier of f and product Fourier of g. So, if we take the Fourier inverse of this product of the Fourier transforms, then we get back to the convolution of these two functions. Well, now the Parseval's identity for the Fourier transforms we will discuss. And here suppose this f star and this g star are the Fourier transforms of this f and g respectively, then what we have these results. So, the integration over this product of this f hat and g hat, and this is a complex conjugate here, is equal to the integral minus infinity to plus infinity, the product of f and g, and again this complex conjugate of this g. So, dx. So, that is the result of this Parseval's identity for the Fourier transform, and as a special case we will see that we can also write this as f hat the absolute value square, and here also the absolute value of this f is square integral from minus infinity to plus infinity, again their integral from minus infinity to plus infinity. So, what we now use the inversion formula for the Fourier transform to get back to these identities. That means, if we take this f x and g, the complex conjugate of this g dx, then what are we getting now, again minus infinity to plus infinity f as it is. For g we are writing the inversion formula. So, for g x the inverse Fourier transform says that this will be 1 over 2 pi and then minus infinity to plus infinity, and we have this g x, and exponential I alpha x with negative sign. So, g x, that means g hat alpha. So, this is the inverse Fourier transform g hat alpha e power minus I alpha x and d alpha. So, this is the inverse Fourier transform, and then its conjugate when we take. So, the conjugate will go to this integrand there. So, here we have e power minus I alpha x, that will become e power I alpha x, and as a result we have here e power I alpha x, and then g hat alpha, the conjugate will go to g hat alpha, and then we have this dx there. So, we change the order of integration. Now, that is a trick again. So, if we change the order of integration here, instead of d alpha dx, we will make dx d alpha. So, we have dx d alpha there and e power I alpha x, and we have this f x, and this g hat alpha conjugate can go now out of this first inner integral. So, what we have now, we can use the definition of the Fourier transform, because having this outside this integral, the inner integral is over f x e power I alpha x dx with this 1 over square root 2 pi, that is the definition of the Fourier transform. So, what we have f x and g x the conjugate equal to minus infinity to plus infinity, and then g hat alpha, that is there already with complex conjugate, and this inner integral which was 1 over square root 2 pi, and then we have minus infinity to plus infinity f x e I alpha x dx, that has become now this f hat alpha, the Fourier transform of the function f, which is written here now, and then this integral, the outer one, is over alpha, which varies from minus infinity to plus infinity. For the second part, so if we take the two functions equal, that means this f x equal to g x, then what will happen? We have the f x and g x equal. So, in the above formula we have taken now the same function. So, we have this right hand side we have f hat alpha and f hat alpha conjugate, the other side we have the integral of f x and f x conjugate dx. And just recall from the complex analysis that this f x and its conjugate, that is nothing but the f x absolute value square, and here also we have this f hat alpha, the absolute value square. So, this is a direct implication of the earlier result to get this just for the same functions. So, we have the integral, the Fourier transform of the f square with the absolute value is equal to the absolute value of f x square integral from minus infinity to plus infinity. So, that was the Fourier the Parseval's identity for the Fourier transform. These are the references we have used for preparing this lecture, and just to conclude that we have seen the scaling property which says that the Fourier transform of f a x is equal to 1 over the absolute value of a and the Fourier transform of this x, which was, so the Fourier transform of this f x was denoted by the f hat alpha. So, in this alpha now the alpha over a will appear, and then this factor will go out. There was a shifting property which says the Fourier transform of f x minus a, then there will be additional factor here e power I alpha a out, and then we have the Fourier transform of f x. The duality property which says here that this Fourier transform of this f hat x equal to f minus alpha. Derivative property, which is the most important now for the application point of view to solve a partial differential or the ordinary differential equations, that the Fourier transform of the nth order derivative of the function is equal to minus I alpha and this power n and the f hat alpha. And remember this property, the most important result which is used to get this nice property was that f goes to 0 as x goes to plus infinity or minus infinity. The convolution property, it is very much used for getting the inverse transform, and later on we will see in many examples that the Fourier transform of the convolution of this f and g is equal to the product of the Fourier transform of f and g. And then at last we have also seen this Parseval's identity, which says that the integral over this alpha of the product of this Fourier transforms of f and g having this complex conjugate over g, then this is equal to the integral of the product of the function, which is f x and the complex conjugate of this g. So, that is all for this lecture, and I thank you for your attention.